All right, I want to do a 4-bar problem using the methods of 6.8. And so let's take a look at a 4-bar that's we've got a rigid body link here, and it's coupler's rigid body, and then we have an output link here that's compliant. It's pinned to the coupler link, and then it's got a compliant link that's rigidly attached to ground. And so this is going to give us a pseudo-rigid body model that looks something like this. And this will be our 4, and if this is L, then R4 is just gamma L. And then R3, R2 are just what they were. Okay? And just to do a fairly straightforward example, we'll have a torsional spring right there to represent the stiffness of that beam. Let's see what kind of, if we put a just a force, say halfway up link 2, okay, and let's make it a horizontal force. That'll, okay, so that'll be cap x2, and then we'll have a torque here. We'll have a spring constant K4, and so what that gives us is if we look at all the different things that we can have, we're looking at this, we're going to want to use, say, equation 6.128 to get the force equation for this thing. And so that's just A plus B d theta 3 d theta 2 plus C d theta 4 d theta 2 equals 0. And with this particular example, we can take a look at A, and let's see here. A equals minus x2 A2. Okay, so we definitely have an x2. So this is going to be, we're going to look at the terms we have from equation 6.123. And the first term we have, but then we don't have any other terms, and that gets multiplied by sine theta 2. And then we have minus x2 times b2 cosine theta 2, and then plus m2 t1 t2. We don't have any of those, okay? And so it's worth asking, what is this A2 and B2? And if we look at this, I said x2 acted halfway up R2, so A2 equals R2 over 2, and B2, well, that's just the offset perpendicular to the link, and that's equal to 0 in this case. So actually, that term goes away. Okay, so we just get one term for A. For B, I go down the list of those. I've got an X3, a Y3, don't have any of those. I don't have an M3. I don't have a T2 or T3 in this. So the B component in my equation is going to be 0. Okay, and that means that there's none of these that are associated with link 3, and that makes sense because if I look at my diagram there, nothing's really happening on link 3. And then I've got C, and I don't have, so this would be equation 6124, how that simplifies down. We're now looking at equation 6125, equation for C. We don't have x4 or y4. We don't have an m4 or a t3, but we do have a t4. So this is just, C is just equal to t4, which is equal to k4 psi 4. And so that's just going to be equal to k4 theta 4 minus theta 4 naught. Okay, and so we can just plug those into our equations. Okay, our values of A, B, and C, and what we'll get is minus x2 r2 over 2 sine theta 2 plus b is equal to 0, so that term goes away. Then we'll have k4 theta 4 minus theta 4 naught, and then we'll multiply that by d theta 4 d theta 2, and that's going to be equal to 0. And so what I can do is I want to isolate this for this x2 because I want to know how big of a force it's going to take to move this 4-bar. Okay, and so what I'm going to get is x2 is going to be equal to k4 theta 4 minus theta 4 naught, h42, that's the same as d theta 4 d theta 2, and then we're going to have 2 r2 sine theta 2, and we can expand the h42 term. That's just equation, we can get that from equation 630. So we can use 6130 right there to substitute for h42, and that'll give us 2 k4 theta 4 minus theta 4 naught, and then we'll have r2 sine theta 3 minus theta 2 equals r4 sine theta 3 minus theta 4, and oops, we had a r2 sine theta 2 as well. Now those r2's can cancel out, and so we've got an expression here for that horizontal force, the magnitude of a horizontal force required to deflect that spring, that compliant member. And now that's a fairly complicated expression, but it really wasn't that hard to get out of this. And so a lot of the work has been done for you in terms of deriving this equation because of having those A, B, and C terms already computed. Okay. Now, a few obvious things that come out of this is that this horizontal force, this force that we need to deflect this, is going to go to 0 anytime theta 4 equals theta 4 naught. It will also go to 0 anytime theta 2 equals theta 3. And so it turns out that a lot of the times you can make this thing right here can fairly easily be made bistable, which means it'll have 3 positions that it'll hold without putting a force. Okay. The first position, assume that this position where I've got shown is where the spring is undeflected. Okay. Then there will be another position, you can imagine, where links 2 and 3 are just kind of mirrored about this line right here. And so that gets this angle for theta 4 back to where it is right now. Okay, so this could be a first stable position. We'll talk about this when we do bistable mechanisms, but just kind of get a feel for this. You can see this is where theta 4 equals theta 4 naught. And we can get another position there where theta 4 equals theta 4 naught. The other equilibrium position we could get out of this mechanism happens when theta 3 equals theta 2. Okay, and what that's going to look like is when R2 and R3 are collinear, and this link is bent like this, and this one's unstable because what happens is the force acting on that pin right there has to travel directly along that line, because I have two force members, and there is a position where that force will travel right along that line, and it isn't that there's no force, because this compliant member definitely is deflected, so it's wanting to move, but it's the force will be parallel with the links, and it won't be able to. There's a unstable equilibrium position. If you have enough friction in that pin there, it'll actually hold, but really what happens here is you can think of this as the boundary between whether this four-bar is going to snap into an upward position or a downward position. Okay, and it's pretty tough to hold it right at that middle position, which is why we call that an unstable equilibrium position.